the biggest cosmic encounter since Oumuamua, and honestly, the world's most powerful space agencies have gone completely dark. On October 3, 2025, an interstellar comet named 3I Atlas buzzed Mars, and the only proof we have is a ghostly smudge found by citizen scientists in public data. With billions of dollars of technology pointed right at it, the official images are missing in action. So, are we looking at a cover-up, a colossal failure, or the quiet prelude to a discovery that will change everything? Let's explore this together. The Flyby. So, what really went down on October 3, 2025? Imagine an object born in the dark between the stars, wandering for millions of years, finally entering our solar system. This visitor, 3I Atlas, made its closest pass to Mars at a distance of just under 0.2 astronomical units. That is about 29 million kilometers, close enough to give us the best look we have ever had at an interstellar object. This wasn't some distant blurry dot. The comet was right in the neighborhood of our most advanced robotic explorers. Experts like Dr. Casey Leese have spent their careers waiting for a moment like this. In response, a fleet of spacecraft was mobilized. NASA's Mars Reconnaissance Orbiter, the European Space Agency's Mars Express, the UAE's Hope Probe, and China's Tianwen-1 all had their schedules scrambled. Mission planners worked overtime, recalculating trajectories to point their instruments at this fleeting target. The comet was moving at a speed no solar system object could match, a ghost passing through the Martian sky. The opportunity was historic, but it was also incredibly brief. The promise of Mars. This was never just about getting a cool picture. This alignment was a once-in-a-generation chance to answer some of the biggest questions in planetary science. Having a world-class laboratory already in orbit around Mars meant we could study 3I Atlas in ways impossible from Earth. Think about it. The Mars Reconnaissance Orbiter's high-rise camera could potentially see the comet's nucleus or any fragments breaking off. Spectrometers like Omega on Mars Express or the Nomad instrument on the Trace Gas Orbiter were ready to taste the comet's atmosphere. Dr. Nicholas Thomas, who leads the team for the CASIS camera, knows these instruments are sensitive enough to detect the unique chemical fingerprints of interstellar ice. Are the building blocks of life the same in other star systems? Is the water in this comet similar to ours? These instruments were designed to answer exactly those questions by analyzing the gases in the coma. It was a chance to perform a chemical autopsy on a pristine sample from another star system, testing every theory we have about how planets are made. Every asset was pushed to its absolute limit for this cosmic flyby. A faint signal emerges. With the world's major space agencies completely silent, the first piece of evidence came from where nobody expected it, the public data archives. Working independently, two citizen scientists known for their meticulous work processing raw space images made the first confirmation. One of them was Kevin M. Gill, a software engineer at JPL who is famous in space circles for turning raw data into art and science. They downloaded the public Mastcam Z images from the Perseverance rover just hours after they arrived on Earth. The process was painstaking. They took dozens of long-exposure images of the Martian night sky, carefully aligned them using the background stars, and then used complex algorithms to subtract the immense noise. And then, they saw it. At the exact predicted coordinates for 3I Atlas, a faint, diffuse patch of light emerged from the static. It is not a dramatic photo. It is a subtle, slightly smeared glow, but it is real. They released their findings cautiously, sharing their annotated images and the code they used so anyone could verify their work. It was a testament to open data and persistent curiosity. The auditable path. Seeing a faint smudge in an image is one thing, but proving it's actually an interstellar comet and not just, say, noise, is a whole other challenge. The path to this detection had to be fully auditable, which means every single step was carefully documented and reproducible. The analysts started with raw 29-second exposures from Perseverance's Mastcam Z camera. The principal investigator for this camera, Dr. Jim Bell, designed it for, honestly, incredible scientific precision. For each image, a T-ratio R-browser R-derby and omichinrostans ambassadorium. Hard-showing had to find a matching dark frame, that's an image taken with the lens cap on, to map out and subtract the camera sensor's own electronic noise. Then flat field corrections came next to account for dust on the lens and any variations in pixel sensitivity. After that, they had to align, or register, every image with sub-pixel accuracy against a star catalog. Only then could they stack the dozens of cleaned frames together. They actually used multiple methods to combine these images, which boosts the signal of a faint object while averaging out random noise. The final step? Modeling and subtracting the Martian sky's background glow. What was left was the detection, a signal statistically strong enough to be real. This wasn't guesswork, it was a forensic process start to finish. Viral myths and reality checks. The moment the legitimate faint signals started to circulate, the internet did what it does best. It found fakes that were, well, way more exciting. The most viral was this sharp, bright streak in a Perseverance navcam image from October 3rd. People claimed it was the comet, clearly visible and dramatic. But seasoned analysts immediately got skeptical. Planetary geologist Emily Lakdawala, who's known for her forensic checks of space images, ran the numbers. She plugged the image time and coordinates into JPL's Horizons system, which is really the gold standard for locating objects in the solar system. The streak's path, speed, and timing matched Phobos, Mars's inner moon, caught during a long exposure. Classic case of mistaken identity. Another claim focused on a different bright streak, but analysts quickly showed it was moving at least 10 times faster than the comet's predicted speed across the sky. So, it was likely a meteor, or maybe even a cosmic ray, hitting the sensor. Emily and others methodically debunked these claims, showing side-by-side comparisons of the fake streaks versus the comet's actual predicted path. The lesson here is pretty clear. In the age of instant analysis, rigorous verification matters more than ever. The silent orbiters. So, where were the multi-billion-dollar orbital missions while citizen scientists were making the only public detection? The silence is honestly what makes this story so strange. Let's be clear about what we're missing. The Mars Reconnaissance Orbiter carries the HiRISE camera, a telescopic instrument so powerful it can spot a coffee table on the Martian surface from 300 kilometers up. Its principal investigator, Dr. Alfred McEwen, and his team could have delivered the sharpest image of an interstellar object ever seen. The ESA's orbiters were ready to perform a chemical analysis. The Trace Gas Orbiter can detect atmospheric gases in trace amounts. If 3I Atlas was venting anything unusual, any molecule not seen in our own comets, it would have found it. The UAE's HOPE and China's Tianwen-1 were also observing, providing a global network of coverage. The potential for a breakthrough was immense. Yet, as of today, not a single raw image, spectrum, or even a low-resolution thumbnail has been released to the public. The data is either under embargo, stuck in a processing queue, or, well, maybe something else is going on. The knife's edge. Pointing a deep space orbiter is not like using a DSLR. It's, really an exercise in calculated risk, operating on what engineers call the knife's edge. The predicted position of 3I Atlas, its ephemeris, was constantly being updated. Each orbiter had to be slewed, or turned to point at a patch of empty sky, just hoping the comet would arrive on schedule. There's no real-time joystick. The commands are sent hours in advance, and the spacecraft executes them autonomously. It is, honestly, a leap of faith. The entire observation might hinge on a prediction that was off by just a fraction of a degree. Then there's the Deep Space Network, the communication lifeline to Earth. According to Dr. Lori Glaze, NASA's head of planetary science, bandwidth is a precious resource. All of NASA's Mars missions plus international partners have to share time. So even if an orbiter captured a perfect image, that data might sit in its onboard memory for days, waiting in line behind higher priority health and safety telemetry. A missed pointing window or a delayed downlink could mean the difference between a historic image and a frame full of empty space. Blinded by the sun. Just as the mystery of the missing data deepened, the curtain came down on any new observations from Earth. And you know, this isn't a conspiracy, it's just orbital mechanics at work. As October advances, 3I Atlas is approaching what's called superior conjunction, when it passes almost directly behind the sun from our perspective. This celestial alignment, happening around October 21st and 22nd, effectively blinds us. The sun's overwhelming glare makes it impossible for any ground-based or near-Earth telescope to safely observe the comet. The comet's most active phase, its closest approach to the sun, or perihelion, happens on October 29th, right in the middle of this blackout. As Dr. Michael S. P. Kelly has noted in his research, this is the most critical time to observe a comet for outbursts. It's when the comet should be at its most dynamic, and we are completely unable to watch. This blackout will last until early December, so for now, the silence from the Mars orbiters is compounded by a physical barrier. The universe itself has blocked our view, leaving us to wonder what is happening in the glare. The working hypothesis. Before the data blackout and the mysterious silence, what did scientists actually think 3I Atlas was? Based on early observations, a working hypothesis had formed. The evidence suggested it was a natural interstellar comet, not an artificial object like some had speculated about Oumuamua. Its behavior was broadly comet-like. Analysis of its light signature pointed to a composition rich in carbon dioxide gas. What was more interesting was what seemed to be missing. Like the previous interstellar visitor 2I Borisov, which was studied extensively by scientists like Dr. Dennis Bodowitz, 3I Atlas appeared to be depleted in dicarbon. This is the molecule that gives most solar system comets their classic green coma. Its absence suggests a different chemistry, born in a different kind of stellar nursery. Some early unconfirmed spectra even hinted at an excess of certain metals, like nickel. But all of this remains provisional. Without the high-fidelity spectra from the Mars orbiters, this hypothesis is just an educated guess. The final word on the comet's chemistry is locked away in the very data we are all waiting for. What remains and what comes next? The data from the Mars flyby might be out of reach for now, but the story is not over. There are a few long-shot possibilities for observation during the solar conjunction blackout. The SOHO spacecraft, which constantly stares at the sun, has a coronagraph called LASCO C3 that might catch a glimpse of the comet. It's not very sensitive, so it would only see 3I Atlas if the comet had a major outburst and brightened dramatically. Farther out in the solar system, the European Space Agency's JUICE spacecraft is on its way to Jupiter. Experts like Dr. Geraint Jones have confirmed that there might be a brief window in early November where JUICE could try to image the comet, but the real action will begin in late November or early December. That's when Earth's motion carries us out of the solar glare, and ground-based telescopes can finally get back in the game. When that happens, expect every major observatory to be pointed at that patch of sky, trying to recover the faint, receding visitor. Until then, the only confirmed public detection remains that single, faint stack of images from Perseverance. So, here we are. We stand on the edge of a potentially historic discovery, armed with more questions than answers. The only public evidence of 3I Atlas's Martian encounter is a faint signal teased from public data by curious minds, while the most powerful instruments in the solar system remain mysteriously silent. Is this a simple case of bureaucratic delay and the unforgiving realities of deep space communication? Or is the data so groundbreaking that it requires absolute certainty before being revealed? The truth is locked on a hard drive millions of miles away. What we do know is that the universe sent us another postcard from a distant star, and we are still waiting to read it. Don't forget to like, Rauwan Skrmeinstradais, till den stu scribe, Rauwat onfine sovri, ondatain sken en bobrabine sten, redan spurs, and hit the bell icon for more deep dives into the mysteries of our cosmos. Thanks for watching Space Facts. A Harvard scientist is sounding the alarm. An interstellar visitor, 3I Atlas, is shedding metallic alloys that just shouldn't exist. Real data from our best telescopes shows atomized nickel streaming from its core, but with practically zero iron, a chemical fingerprint that really defies everything we know. Harvard's Avi Loeb is asking the question no one else wants to: if these metals aren't natural, what does that mean? The answer could upend our place in the universe, so let's explore this together. The discovery of 3I Atlas. What would you do if you saw something moving at 130,000 miles per hour that wasn't supposed to be there? On July 1st, 2025, the Atlas survey team in Chile spotted a faint, fast-moving speck. The math instantly told a story that just didn't fit any known playbook. Its path wasn't just a long loop, it was hyperbolic, with an extreme eccentricity that confirmed it was a visitor from deep space. moving too fast for the sun to ever capture it. This wasn't a comet on a return trip. Astronomers combed through archival data and found earlier images, firming up its trajectory. The object was born far beyond our solar system, possibly somewhere near the galactic center. By the time it was discovered, it was already inside Jupiter's orbit, making a one-time slingshot around our sun before it shoots back into the void. Its incredible velocity confirmed it. 3I Atlas is only the third confirmed interstellar object ever seen, a messenger from another star that will never return. This isn't just a rock, it's a clue from an unknown part of the galaxy. The Nickel Mystery. Imagine finding a fingerprint that doesn't match any person on Earth. That's what astronomers found in the light from 3I Atlas. Almost as soon as it crossed Jupiter's orbit, spectrographs detected strong signals of atomic nickel streaming from its coma. But the real shock wasn't what was there, it was what was missing. There was virtually no iron. This isn't just unusual, it's chemically bizarre. In every meteorite and comet we've ever studied, nickel and iron are cosmic partners, forged together in the hearts of dying stars and locked into the same minerals. When a comet heats up, they should be released together. Yet, data from the Very Large Telescope showed nickel vaporizing off the object, while iron was a no-show. Harvard astrophysicist Avi Loeb was the first to publicly highlight how unnatural this is. He argues that separating nickel from iron requires industrial processes here on Earth. In space, it's unheard of. It's like finding a gold ring without any trace of the other metals typically alloyed with it. This single chemical clue is so potent that it forces a profound question. Are we witnessing a freak of nature, or is this a deliberate engineered signature? Carbon dioxide dominance. Just when the nickel-iron problem had scientists scrambling, the James Webb Space Telescope delivered another bombshell. Pointing its powerful infrared instruments at 3I Atlas, a team of astronomers analyzed the gases in its coma, and found that carbon dioxide was completely dominating the mix. The measured carbon dioxide to water ratio was a staggering 8-to-1, the highest ever recorded for any comet, whether from our solar system or beyond. To put that in perspective, typical solar system comets have CO2 levels around 4% of their water content. Here, CO2 is the main ingredient. This wasn't a fluke. The readings remained consistent across multiple observation sessions as the object neared the sun. While other gases like carbon monoxide were present, nothing came close to the CO2 spike. This kind of chemistry just doesn't align with our models of comet formation. Some researchers propose that its unique composition is the result of being cooked by cosmic rays over a billion-year journey. Others wonder if it's a clue to the specific conditions of its home star system. But the question remains, does this unprecedented chemistry point to nature at its most extreme, or is it another sign that something else is at play? The Oumuamua precedent. This isn't the first time an interstellar visitor has broken all the rules. Back in late 2017, astronomers detected one Oumuamua. At first it seemed like an asteroid, but its behavior was deeply strange. As it swung past the sun, it began to accelerate, pushed by a force that wasn't gravity. The problem? There was no visible outgassing, no tail, no coma, none of the typical rocket-like effects a comet uses to speed up. Oumuamua left nothing behind. Its light curve also suggested a bizarre shape, perhaps 10 times longer than it was wide, like a cigar or a flat pancake. The scientific community scrambled for an explanation: exotic ices, hydrogen outgassing, fractal dust. But no single natural theory fit all the data. It was into this debate that Harvard's Avi Loeb stepped, arguing that Oumuamua's shape and acceleration were consistent with an artificial object, specifically, an ultra-thin solar sail designed to ride the pressure of starlight. The idea caused a firestorm, but it cemented a critical precedent. When objects from other stars arrive, we shouldn't assume they'll play by our rules. Oumuamua prepared the scientific world to ask bolder questions. Ancient sky metal. Humanity's fascination with metals that fall from the sky is not new, it's ancient. Over 5,000 years ago in ancient Egypt, craftsmen hammered tiny beads from a mysterious iron that they didn't mine from the earth. Modern analysis of these beads from the Giza cemetery reveals a nickel content of nearly 30%, far higher than any terrestrial ore. This was the unmistakable signature of meteoritic iron. The story gets even more incredible with the dagger found in the tomb of King Tutankhamun. Discovered in 1925, The pristine iron blade was a mystery for decades. Finally, X-ray analysis confirmed its celestial origin. The blade contained 11% nickel and traces of cobalt, a composition that matched iron meteorites. The Egyptians even had a name for this divine material, iron of the sky. It was rarer and more valuable than gold, reserved for pharaohs. This history matters because it establishes a fundamental contrast. Terrestrial iron ores almost never exceed 4% nickel. Meteoritic iron, however, is rich in it. The same questions our ancestors faced, what is this strange metal and where did it come from, are echoing today as we analyze the impossible alloys of 3I Atlas. Kilonova formation theory. So if not aliens, what could possibly create pure nickel vapor in space? The answer might lie in one of the most violent events in the universe, a kilonova. This is what happens when two neutron stars, the ultra-dense corpses of massive stars, spiral into each other and collide. The resulting explosion is so powerful, it forges heavy elements through a process of rapid neutron capture known as the R process. In 2017, the gravitational wave event GW170817 gave astronomers their first direct look at this process, confirming that neutron star mergers create vast quantities of heavy elements like strontium, gold, and platinum. Nickel is also created in this cosmic furnace. Crucially, depending on the chaotic conditions of the explosion, some models predict that patches of the ejected debris can be exceptionally rich in nickel while being poor in iron. These aren't the slow-cooked metals from normal stars. They are forged in seconds and blasted into space. If 3I Atlas condensed from such a cloud of debris, it would carry a chemical fingerprint completely alien to our solar system. This provides a natural, albeit spectacular explanation for its strange composition. Asymmetric supernova theory. So, there's another natural forge out there in the cosmos, violent enough to potentially explain 3I Atlas's strange chemistry, an asymmetric supernova. You see, not all stars meet their end in neat spherical explosions. Some, well, they rip themselves apart in these lopsided blasts that fling elements out in jets. The supernova remnant W49b is a perfect example of this. X-ray maps from the Chandra Observatory show that iron is packed tightly near the remnant's core, while other elements like sulfur and silicon are distributed more broadly. This kind of uneven explosion, it completely changes the rules of how metals are scattered into space. In these chaotic events, the inner layers of the star, where iron and nickel are made, don't mix evenly. Instead, high-speed plumes can punch through the star's outer layers, carrying specific elements with them. And if nickel happens to be concentrated in the path of one of these jets, it can be ejected in bulk, leaving most of the iron trapped behind. So, if 3I Atlas formed from a fragment blasted out by such a supernova, it could have started its journey as a chunk of nearly pure nickel. This provides a second plausible, though very rare, natural path to its bizarre composition. Statistical improbability. Beyond its strange chemistry, the path of 3I Atlas through our solar system is so unusual it's hard to ignore. Avi Loeb and his collaborators ran the numbers, calculating the probability that a random interstellar object would have a trajectory that takes it unusually close to Venus, Mars, and Jupiter, all in a single pass. The result was a probability so small it's almost zero, about 0.005%. That's like flipping a coin 15 times and getting heads every single time. To Loeb, this really strains the definition of coincidence and starts to look like a pattern. The object's path is nearly flat relative to the solar system's plane, but it's moving backward or retrograde against the flow of the planets. This combination allows it to skim past the inner worlds in a way that looks suspiciously like a survey flight. Critics argue that in a vast universe, rare events are bound to happen, but Loeb counters that if the odds are 1 in 20,000, and we've only seen 3 interstellar visitors so far, something doesn't add up. When you combine this improbable trajectory with the engineered-looking metals, Loeb argues it's time to take the artificial origin hypothesis seriously. The Golden Record Parallel. Could 3I Atlas be a message in a bottle? In 1977, NASA launched the Voyager 1 and 2 spacecraft, each carrying a golden record. This was a project led by Carl Sagan, intended as a time capsule for any extraterrestrial civilization that might find it thousands of years from now. The records contain sounds and images of Earth, music from various cultures and scientific diagrams, a snapshot of humanity etched onto a durable physical object. Sagan said, "The launching of this bottle into the cosmic ocean says something very hopeful about life on this planet." Now consider 3I Atlas, an object loaded with alloys and compounds that don't fit natural recipes on a trajectory that seems too precise. The parallel is striking. What if its message isn't written in grooves on a record, but in the very ratios of its elements? A physical archive designed to survive a journey of millions of years. If its composition is intentional, then 3I Atlas isn't just a visitor. It's a courier carrying a record of another world's chemistry, and maybe even its technology. Atomic messages. What if we've been looking for the wrong kind of message? For decades, the search for extraterrestrial intelligence has focused on radio waves and light signals. But what if an advanced civilization chose to send a message encoded in matter itself? This is the provocative idea that the anomalies of 3I Atlas force us to consider. On Earth, scientists are already developing methods to store information using the ratios of isotopes in molecules, creating a kind of atomic fingerprint that can be read with a mass spectrometer. In biology, DNA stores vast amounts of information in a sequence of 4 chemical bases. Some theorists now wonder if the periodic table itself could be used as a sort of cosmic QR code. By arranging isotopes in a pattern that nature would never produce by chance, a message could be baked into a physical object. This message would be incredibly durable, immune to cosmic noise, and capable of surviving for billions of years. Spectrographs are now re-examining every bit of data from 3I Atlas, looking for these hidden patterns. The hunt is on for a fingerprint that says someone was here, and they wanted to be found. The story of 3I Atlas leaves us at a profound crossroads. On one hand, we may be witnessing an undiscovered violent natural process, a kilonova or an asymmetric supernova capable of creating alloys we once thought impossible. On the other hand, the combination of inexplicable metals, extreme chemistry, and a statistically improbable trajectory has forced serious scientists like Avi Loeb to consider an engineered origin. This isn't just a theoretical debate, it's a real object with real data that is breaking our models of the universe. Either way, our understanding has to expand. Don't forget to like, subscribe, and hit the bell icon for more deep dives into cosmic mysteries. Thanks for watching Space Facts. Could an object speeding through our solar system from the void between the stars actually be an alien spacecraft? On July 1, 2025, a mysterious visitor designated 3I Atlas was discovered, sparking a fierce debate. Was it a natural comet, or the first definitive proof of extraterrestrial technology? One prominent Harvard scientist fanned the flames of speculation, while NASA pushed back with hard data. What followed was a clash between radical ideas and rigorous evidence. Let's explore this together. The Atlas discovery in Chile. So how do we even spot these interstellar travelers in the first place? It starts with a constant, vigilant watch of the night sky. The story of 3I Atlas began on July 1, 2025, at an observatory in Chile. There, a robotic survey system named ATLAS, which stands for Asteroid Terrestrial Impact Last Alert System, detected a faint object at an apparent magnitude of 20, making it about 2.5 million times fainter than the faintest star visible to the naked eye. Led by principal investigator John Tonry, the ATLAS system is a NASA-funded project developed by the University of Hawaii, using its twin half-meter telescopes to scan the entire visible sky every 24 hours. When astronomers calculated the object's trajectory, they saw it was following a sharply hyperbolic path with an orbital eccentricity greater than 1, a definitive sign it wasn't gravitationally bound to our sun. Its orbit was an open curve, meaning it came from deep space and was destined to return there. The object was named 3I Atlas, with the 3I marking it as the third interstellar object ever discovered. It was racing through our system at a stunning hyperbolic excess velocity of 35 kilometers per second, a truly exceptional catch and a prime target for immediate scientific study. Avi Loeb's controversial hypothesis. But what if a new discovery doesn't fit neatly into our existing boxes? This is where science can get heated. Enter Avi Loeb, a Harvard astrophysicist and the head of the Galileo Project, an initiative dedicated to searching for evidence of extraterrestrial technology. Having previously sparked debate by suggesting the first interstellar object, Oumuamua, could be artificial due to its observed non-gravitational acceleration, Loeb turned his attention to 3I Atlas. He pointed to its early lack of a visible tail and what he described as a trajectory that might eventually show subtle deviations not caused by gravity. In a paper released on the ArcZiv preprint server, a common practice for rapidly disseminating new ideas, he proposed his radical hypothesis. If the object continued to show no outgassing, it might be a technological artifact. He even raised the hypothetical possibility of malign intent, suggesting it could use the sun for a gravitational slingshot to alter its course towards an undisclosed target. Loeb was careful to frame this as an intellectual exercise, admitting a natural comet was the simpler explanation. Still, the mere mention of alien technology from a scientist of his stature was enough to ignite a global media firestorm and put serious pressure on the astronomical community to respond. Media sensation versus scientific method. Here's the thing about alien theories. They travel faster than light speed in the media. Avi Loeb's hypothesis for 3I Atlas was sensational. Headlines around the world, from online blogs to major news networks, quickly latched onto the most dramatic elements of his proposal, the possibility of an alien craft with potentially hostile intentions. This created a fascinating public spectacle but also highlighted a fundamental tension in how science works. The scientific method is a slow, methodical process that can take months or even years of observation and peer review before any conclusion is reached. In stark contrast, the news cycle operates in mere hours. The global conversation was suddenly centered on a dramatic, unproven idea while the painstaking work of collecting hard data was just beginning. This put NASA in the position of having to respond not just to a scientific hypothesis, but to a worldwide media event fueled by one of the most compelling questions in human history. It was a classic case of exciting speculation, published on a preprint server before peer review, getting a massive head start on the deliberate evidence-based investigation. This gap between speculation and verification is where misinformation can thrive. NASA's comprehensive investigation. When a claim is that big, you really need the world's premier space agency to weigh in. So how did NASA approach the mystery of 3I Atlas? Well, they didn't rely on just a single instrument. Instead, they launched a coordinated, multifaceted observation campaign, allocating dozens of hours of precious observation time on their flagship observatories. This involved the Hubble Space Telescope, using its Wide-Field Camera 3 to capture incredibly detailed visible light images, and the James Webb Space Telescope, using its NIRSPEC instrument to analyze the object's infrared light for chemical signatures. A network of powerful ground-based observatories, like the Keck Observatory in Hawaii with its massive 10-meter twin telescopes, also joined the effort to track it continuously. This wasn't just about taking pictures. The goal was a deep analysis under the guidance of experts like Dr. Karen Meach, a leading astrobiologist renowned for her work on distant comets. This comprehensive approach was designed to replace speculation with an overwhelming body of evidence. NASA's mission was clear: to determine, with the highest possible degree of scientific certainty, the true nature of this interstellar visitor and let the data tell the real story. Comet behavior confirmed. So what does a comet actually do when it gets close to the sun? The answer to that question was the key to solving the 3I Atlas mystery. As the object continued its journey inward, NASA's array of telescopes watched its every move. The findings were unambiguous. By late July 2025, as it crossed inside the orbit of Mars, 3I Atlas started to behave exactly like a comet. It developed a glowing coma, a fuzzy atmosphere of gas and dust, that eventually grew to over 100,000 kilometers in diameter. Soon after, it began to sprout a tail of dust and gas stretching for millions of kilometers, pushed away from the nucleus by the solar wind. Dr. Lori Glaze, director of NASA's Planetary Science Division, summarized the findings clearly, stating that the object was exhibiting all the classic signs of a comet, reacting to the sun's energy. Its initial lack of a tail was simply because it was too far from the sun for its ices to sublimate. The final verdict from the data was it looks like a comet, and it acts like a comet, so there was no need for an exotic, artificial explanation when a natural one fit the observations perfectly. Chemical composition analysis. Here's what really matters. You can learn a lot about something by the light it gives off. Using a technique called spectroscopy, a team of astrochemists led by a figure like Dr. Stephanie Malam from NASA's Goddard Space Flight Center analyzed the chemical makeup of 3I Atlas. This process is like a cosmic fingerprint analysis, where light from the comet's coma is split into a spectrum, revealing the distinct signatures of the molecules within it. The analysis confirmed the presence of water ice, but it was the other volatiles that were truly telling. They found a carbon dioxide to water ratio of 0.6, nearly double the average for comets in our solar system. The data from JWST also revealed significant amounts of carbon monoxide and traces of diatomic carbon, the molecule responsible for giving many comets their distinctive green glow. Far from being evidence of artificial design, these unique chemical traits told a story of its origins. The high CO2 content suggested that 3I Atlas formed in a brutally cold region of its home star system, much farther from its parent star than where our own comets were born. It was a pristine sample from a truly alien yet completely natural environment. Trajectory and safety assessment. With all the talk of alien technology and malign intent, a critical question had to be answered. Was this object a threat to Earth? The bottom line is a definitive no. NASA's Jet Propulsion Laboratory, or JPL, used the global observation data to refine the comet's trajectory with pinpoint accuracy. Their calculations made public through the Center for Near-Earth Object Studies showed its closest approach to Earth would be a distant 1.8 astronomical units, which is roughly 170 million miles. There was never any risk of impact. The comet's orbit was also highly inclined at 60 degrees relative to the ecliptic plane, the flat disk where the planets orbit, meaning it was passing high above the main traffic of the solar system. Its perihelion, or closest approach to the Sun, was calculated to be a safe 1.5 AU, well outside of Earth's orbit. NASA's Planetary Defense Coordination Office was therefore able to declare with certainty that this object posed zero threat. This precise tracking dismantled any notion that the comet could be a danger, allowing everyone to focus on the science. Natural anomalies in cometary physics. But what about the unusual traits that sparked the controversy in the first place? It's important to remember that in astronomy, unusual does not automatically mean unnatural or artificial. Comets, even the ones from our own solar system, are, notoriously unpredictable. To provide some context, NASA pointed to historical examples like Comet 17P Holmes. Back in 2007, that comet suddenly brightened by a factor of nearly 1 million in less than 48 hours, totally shocking astronomers as it briefly became the largest object in the solar system by volume. This was a completely natural outburst, not an artificial maneuver. Cometary physicists like Dr. Michael Kelly from the University of Maryland explain that these events happen when sunlight penetrates a comet's crust and hits a pocket of super volatile ice, like frozen carbon monoxide, causing it to flash sublimate and release enormous amounts of gas and dust. These anomalies are not evidence of intelligent control, they are actually a normal and expected part of cometary physics. The strange initial behavior of 3I Atlas wasn't a sign of technology, it was a sign that it was a dynamic natural object. Scientific value of interstellar visitors. So, if it's not an alien ship, why is 3I Atlas still such a big deal? Well, because its scientific value is immense. Every interstellar object that passes through our solar system is like a pristine time capsule delivered from another star. These objects carry the unique chemical and physical fingerprints of the planetary nursery where they were born. The high concentration of carbon dioxide in 3I Atlas tells us it likely formed in an incredibly cold, distant region of its home system. Some studies even suggest it could have originated in the Milky Way's thick disk, a population of older stars, making the comet potentially over 7 billion years old, actually predating the formation of our own sun and planets. Scientists could test this hypothesis by analyzing its isotopic ratios, for instance, the ratio of carbon-12 to carbon-13, and comparing it to other stellar populations. That makes it more than just a passing rock. It's a preserved fragment from the dawn of another world, providing invaluable data for our models of galactic chemical evolution. Comparing 3 interstellar objects. Let me explain why having more than one of these visitors is so crucial. By comparing them, we can start to build a bigger picture of the galaxy. 3I Atlas was the third interstellar object detected, and it's fascinating how different all 3 have been. The first, 1E Oumuamua, was highly anomalous, rocky. appearing to have an extreme 10-to-1 aspect ratio, and showing no visible coma, which is what led Avi Loeb to his original theory. The second, 2I Borisov, discovered by amateur astronomer Gennady Borisov, was almost the opposite. It looked and behaved very much like a standard long-period comet from our own Oort cloud, with a chemical composition, specifically a carbon monoxide to water ratio of about 0.3, that was remarkably familiar. 3I Atlas falls somewhere in the middle. It clearly behaves like a comet, but its distinct chemical ratios and light-scattering properties make it stand out as unique. This diversity is exactly what astronomers hope to find. It allows them to test whether the processes that shaped our home system are typical, or if we are, an outlier. In the end, Comet 3. I-Atlas wasn't an alien messenger, but it did bring an incredible message. It wasn't science fiction, but it delivered profound science. It carried the chemical secrets of its birthplace, a star system far from our own, giving us a rare glimpse into the diversity of worlds forming across our galaxy. The real story isn't about a manufactured object, but about the natural wonder of the universe and our growing ability to study it. If you want more deep dives into the biggest discoveries from space, don't forget to like, subscribe, and hit the bell icon. The universe always has another surprise waiting for us. Thanks for watching Space Facts.